In 1955, the United States Navy unleashed a beast, the USS Forrestal. It was the world's first true supercarrier, stretching 1,063 feet long and 252 feet wide. It displaced 81,000 tons of American steel. It was the physical embodiment of a superpower that had just saved the world from tyranny, a floating fortress designed to project strength into a new, uncertain Cold War era. Fast forward 62 years to 2017. The Navy launched the USS Gerald R. Ford. It is the most expensive warship in human history, costing a staggering $13 billion. It is a technological marvel, powered by two A-1B nuclear reactors, capable of generating 3 times the electricity of its predecessor. It replaces steam catapults with electromagnetic rails and houses stealth fighters in its hangar. But if you take a tape measure to the flight deck, you will find a number that defies logic. Width 256 feet. Think about that for a moment. In 6 decades of absolute global dominance, the American supercarrier has grown by exactly 4 feet in width. Its length remains virtually identical. Its displacement hit the 100,000 ton mark in the 1970s and then simply stopped. In that same time frame, humanity went from rotary phones to iPhones. We went from the Model T to the Tesla. We moved from propeller planes to hypersonic missiles. Yet the big stick of American diplomacy, the primary tool for global power projection, has been frozen in physical dimensions for over half a century. Why? Why does a military doctrine built on overwhelming force a culture that believes bigger is better, and a defense budget larger than the next 10 nations combined, accept this stagnation? Did we run out of steel? Did we run out of money? Never did we run out of ambition. Impossible. The answer is buried in the concrete and hidden in the mud. The US Navy isn't choosing to keep its carriers at 100,000 tons out of some sense of modesty. They are being held prisoner. They are trapped in what naval architects call the cage. The enemies keeping our ships this size aren't Chinese DF-21 missiles or Russian Cylon torpedoes. The real enemies are physics, geography, and industrial concrete. Today we are going to tear apart the blueprints. If you want to understand the engineering that rules the waves, you have to look at the invisible walls that confine the most powerful weapon system on Earth. We will see why building a mega carrier isn't a sign of strength but a suicide note, and we will discover why 100,000 tons isn't a limit. It is the number of perfection. To understand why we stopped growing, you first have to understand how fast we used to run. The evolution of the US carrier is a story of violent explosions of innovation followed by long calculated silences. In 1922 there was the USS Langley CV-1. To be honest, it was a makeshift experiment. It was a co-op ship, the USS Jupiter, with a wooden roof slapped on top. It displaced 11,500 tons and crawled at 15 knots. It barely had enough speed to generate the wind necessary for biplanes to wobble into the air. It was a joke to the battleships of the era, but it was a beginning. Then came World War II. The shackles of naval treaty limits came off. We built the Essex class, 36,000 tons of war-winning aggression. These were the ships that broke the back of the Imperial Japanese Navy, mass-produced industrial miracles that proved the carrier was the new king of the sea. But then the sky changed. The jet age arrived. Propellers were out, turbines were in, jets were heavy, they were fast, and they were thirsty for fuel. They needed more runway and more catapult power. The Navy responded with the Midway class at 64,000 tons. It was the first American ship too wide to fit through the Panama Canal. We broke our first geographic lock because we needed the size. We didn't care about the shortcut, we cared about the mission. Then came the quantum leap 1955, the Forrestal. This was the moment the supercarrier was born. We jumped from 64,000 tons to 81,000 tons almost overnight. We widened the deck to 252 feet to accommodate the revolutionary angled runway, allowing for simultaneous launches and recoveries. It was a revolution in deck flow and sheer presence. But look at the data after that. From the Forrestal in 1955 to the Nimitz in 1975, the length grew by only 25 feet. From the Nimitz in 1975 to the Ford in 2017, the length grew by virtually zero. The hull form of the US supercarrier has been essentially a photocopied design for 70 years. The Ford isn't a new shape, it is a Forrestal-style hull packed with 21st century technology. Why not build a 150,000-ton ultra carrier? Why not a 200,000-ton floating continent? Imagine the power 150 jets. an unsinkable airfield, a sovereign piece of American territory that could end a war by just appearing over the horizon. It sounds like a dream. But if you try to build it, you run headfirst into the concrete wall. If you want to see the hard limit of American power, you don't go to the Pentagon. You go to Virginia Newport News shipbuilding. This is the only place in the Western Hemisphere capable of birthing a nuclear-powered aircraft carrier. Specifically, you go to Dry Dock 12. This is a massive reinforced concrete pit. It is 2,172 feet long and critically it is 249 feet wide. Memorize that number, 249 feet. Now let's look at the specs of the USS Gerald R. Ford again. Flight deck width, 256 feet. Wait a minute, do the math. The ship is wider than the hole it is built in. It is 7 feet wider than the dock. How do you fit a 256-foot object into a 249-foot box? You cheat physics. You use a technique called the cantilever. The hull of the ship, the part that actually sits in the water, is only 134 feet wide. It fits easily into the pit, but the flight deck flares out. It explodes outward like a mushroom cap. When the ship is being assembled, the edges of the flight deck literally hang over the concrete walls of the dry dock. They hang over the service roads. They hang over the heads of the workers walking on the pier. And here is where the cage slams shut. Running parallel to Dry Dock 12 is a monster called Big Blue. It is the largest gantry crane in the Western Hemisphere, a skyscraper on wheels used to lift 1,000-ton sections of the ship into place. It runs on rail tracks right next to the pit. The gap between the edge of the Ford's flight deck and the leg of the Big Blue crane is measured in inches, not feet, inches. If the Navy wanted to build a carrier that was 150,000 tons, let's say with a 300-foot beam, it simply would not fit. The flight deck would smash into the crane before the ship was even half finished. To build a bigger ship, the United States would have to demolish Dry Dock 12. They would have to tear up the rail lines. They would have to rebuild the entire industrial infrastructure of Newport News. The cost billions. And that is billions of dollars spent before you even weld the first piece of steel for the ship itself. The CVX studies in the 1990s looked at this reality. They realized that the infrastructure cost alone would kill the program before it even began. So the USS Ford is the exact size of the tool used to make it. It is a cast of its own mold. We aren't building the ship we necessarily want, we are building the ship that fits. But let's say we did it. Let's say we spent the billions, demolished the docks and launched a 200,000-ton monster. Congratulations, you have just built the world's largest prisoner because now it has nowhere to go. Aircraft carriers are tools of freedom, and freedom requires movement. But the ocean is not as free as you think. For a ship with a 40-foot draft and the height of a 24-story building, the world is a maze of narrow choke points. The most dangerous one is in Egypt, the Suez Canal. This is the jugular vein of global strategy. It connects the Mediterranean to the Persian Gulf. If a carrier cannot use the Suez, it has to sail around the entire continent of Africa. That adds weeks to response time. It burns millions in logistics and fuel. Worse, it eats away at the precious finite lifespan of the nuclear reactor core before the ship even reaches the fan. Now look at the rule book of the Suez Canal Authority. Maximum allowable beam, 254 feet. Look at the USS Ford again. Its flight deck spreads out to 256 feet. Technically, the ship is already a special operation risk. The flight deck literally hangs over the canal banks as it passes. A sudden gust of desert wind acting on that massive surface area, like a giant sail, can push the 100,000-ton ship into the sand. The pilots don't just steer, they fight the aerodynamics to keep the ship from drifting into a catastrophic grounding. But the trap isn't just the width, it's the ceiling. Look up. Spanning the canal is the Al Salam Bridge. The clearance height is exactly 230 feet. On older ships, the Navy used folding masts to dock under bridges. But the Ford is different. It carries the new dual-band radar, the most sensitive eyes in the fleet. These massive radar panels need a solid, immovable foundation. They cannot shake, and they certainly cannot fold. So the architects faced a brutal constraint. They had to design a 100,000-ton fortress to fit inside a box, defined by a civilian bridge in Egypt. The result is the integrated mast, a fixed composite monolith. It doesn't bow, it doesn't fold, it is sculpted to clear the Al Salam Bridge, but only just. It is a game of inches. Imagine piloting a 24-story building under a concrete beam at 10 knots. If the calculation is wrong or if the tide is unexpectedly high, you don't just lose an antenna battery, the bridge would smash the ship's brain. The Ford fits, but it fits with the terrifying precision of a bullet in a chamber. And the cage gets even tighter when you try to come home. Let's talk about mud. At Naval Station Norfolk, the home of the Atlantic Fleet, the channels are maintained at 50 feet deep, but nature hates depth. Silt and sand fill those channels at a rate of 2 feet per year. The Army Corps of Engineers is on a permanent dredging treadmill, digging 24/7 just to keep the artery open. If we built a 150,000-ton ultra carrier, it would ride much lower in the water. Its draft would likely exceed 45 feet. That destroys the safety margin. A bigger ship would literally be dragging its belly through the mud. It couldn't enter Norfolk. It couldn't enter Yokosuka, Japan. It would be a homeless king forced to anchor miles offshore, relying on smaller boats for every scrap of resupply. The Earth itself has set the limit, 100,000 tons feet. Anything more gets stuck. But the critics still argue, who cares about the canal, who cares about the dock? We need more firepower. We need 120 jets, not 75. This is the Walmart mentality. The idea that buying in bulk always means better value. In naval warfare, this is dead wrong. In the 1990s, the Navy and the RAND Corporation ran the numbers. They looked at designs for large carriers carrying 100 plus aircraft. They found something shocking: the law of diminishing returns. A flight deck is a finite ecosystem. It is about 4.5 acres. If you jam 120 planes onto that deck, you don't get more airstrikes. You get a parking lot. You create gridlock. Aircraft have to be moved just to let other aircraft taxi. The bomb farm gets blocked. The catapults can't cycle fast enough. The metric that matters isn't hangar capacity, it is SGR sortie generation rate. How many bombs can you put on target in 24 hours? The Nimitz class can sustain about 120 sorties a day. The Ford class targets 160. How did they get that 33% increase without making the ship bigger? They didn't look at bigger ships, they looked at NASCAR. They analyzed the pit stop. On the old Nimitz, the bomb farm was in the wrong place. To load a GBU-12 laser-guided bomb on an F-18, aviation ordnancemen had to push bomb carts across the active taxiways. Imagine trying to refuel a race car while crossing the track during the race. It's madness. On the Ford, they moved the island, the command tower, back 140 feet. This opened up a massive pit row in front of the superstructure. They installed advanced weapons elevators that use magnetic motors to shoot bombs straight from the magazine to the flight deck right next to the jets. No crossing traffic, no waiting, land, refuel, reload, launch. It is a closed loop of violence. The Ford generates more combat power than a hypothetical 150,000-ton monster because it is faster, not bigger. It is density over volume, efficiency over excess. But efficiency is only half the story. There is a seductive whisper that haunts the halls of the Pentagon. What if? What if we just broke the rules? What if we built the Titan anyway? When the Navy finally ran those numbers, they didn't see a fortress. They saw a trap. Back in the 1990s, when the Cold War's shadow had finally retreated, the admirals looked at the aging Nimitz hulls and dared to dream beyond the 100,000-ton ceiling. They launched the CVX program to design the ultimate Leviathan, a ship that would carry 120 jets and rule the oceans until the 22nd century. But as the architects drew the lines, the dream dissolved into a nightmare. They realized that building a mega carrier wasn't just an engineering hurdle, it was a strategic suicide note. The first catastrophe is economic, the prototype trap. The genius of the Ford class is that it rests on a legacy. The Navy possesses 50 years of hard data on exactly how a 100,000-ton hull behaves in a North Atlantic storm. We know every stress point, every vibration, every quirk of the steel. If you build a 150,000-ton carrier, you throw that entire library of knowledge into the incinerator. The CVX report warned that a new hull form would reset the industrial learning curve. This causes the cost per ton to skyrocket. You wouldn't be building a standardized warship, you would be building a massive, unproven $25 billion science experiment. In naval shipbuilding, unproven experiments don't just burn money, they burn decades of time. But let's assume the money was no object. Let's say Congress wrote the blank check and we launched this beast. Now you face a darker, more primitive enemy: hydrodynamics. Water is 800 times denser than air. As a ship gets wider, the drag doesn't just increase, it multiplies. To generate enough wind over deck to launch heavy fuel-laden bombers, this massive hull would need to sprint at 30 knots. But the physics of a 150,000-ton displacement make that speed a grueling task. 2 nuclear reactors wouldn't be enough. You would need 3, maybe 4. This creates a death spiral of design. More reactors mean more weight. More weight means more drag. More drag means you need even more power. you end up with a toothless tiger, a ship too fat to run, unable to reach the speeds required to launch its own aircraft on a calm day. And ultimately, even if you could make it run, the Navy realized that you shouldn't. This is the argument that finally killed the Ultra Carrier concentrated vulnerability. Imagine a single vessel that represents 25% of the Navy's entire air power. It carries 6,000 souls and costs more than the GDP of some nations. Now imagine one lucky torpedo or one hypersonic cruise missile slipping through the defensive screen. In 10 minutes you haven't just lost a ship, you have lost the war. You have concentrated too much national power into a single massive target. The Navy did the math and realized the brutal truth: dispersion is survival, concentration is death. They would rather have 11 100,000-ton fighters dispersed across the globe than 6 fat targets waiting to be hunted. So the next time you look at the USS Gerald R. Ford, don't be disappointed that it isn't larger. Don't look at the number 100,000 tons as a limitation. Look at it as discipline. It is the Goldilocks number. It is the perfect balance found after a century of blood, sweat, and engineering trial and error. It is small enough to fit our docks, slim enough to squeeze through the Suez Canal, yet massive enough to project American power to any shore on Earth. The United States Navy didn't choose size. We chose efficiency. We chose to innovate inside the hull with electromagnetic catapults and advanced weapon elevators rather than bloating the hull itself. In a world of excess, enough is the most dangerous word in the dictionary. Too much is a target. Precision is a weapon. This ship is the ultimate machine, a masterpiece of engineering that fits perfectly within the cage of reality. The cage hasn't changed, but the beast inside has become infinitely more lethal.